So next up, we've got William Lesinhovski from the Federal Department of Environment Engineering in Brazil, who will be presenting on a runtime comparison between CHIUW and Fortran.
Thank you, everyone, for being here. I will start my presentation. Runtime comparison between CHIUW and Fortran. This is a beginning research for my postdoc with Professor Nelson. The main objective is to compare the performance of CHIUW and Fortran on a single core and running some algorithms in numerical analysis. We choose matrix vector multiplication, the Lex method for the kinematic wave equation, and the successive over-relaxation method for Poisson equation. The main motivation is we want to develop a code in CHIUW for fluid mechanics simulations, and we want to know if CHIUW has a similar performance with Fortran, which is the most used language for these simulations. For matrix vector multiplication, we can consider the square matrix with size n times n, and we can define the product AX, or on the other hand, the product X transpose A. The first one is the inner product of the X, vector X, with the row of each row of A, and X transpose A, we have the inner product of X with the columns of A. The first one works better with CHIUW because of the row major order, and the second one works better for Fortran because the column major order. Also, we can improve the runtime using low-level routines, and we will test these options. So here the codes using in CHIUW and Fortran. And for the low-level functions, we use the GenV from the BLAS library in CHIUW and matmul in Fortran. So the A is a square matrix. We choose n equals 10,000, and A and X were filled with random values. Here we have the runtime for the codes. AX is faster in CHIUW, and X transpose A is faster in Fortran. But in this case, we have X transpose A faster in CHIUW than AX in CHIUW. For the low-level functions, GenV is the fastest one, is the fast option over we tested. So the kinematic wave equations, we have the domain X in 0, 10 and T in 0, 1. We choose a uniform grid for space and time, and use the Lex method for time advance. So here are the codes in CHIUW and Fortran. We have to take account that the row major order and the column major order. So we have to adapt the codes for each language. Actually, we test the two options for each language. So here the boundary conditions views and the parameters, and saving the values of each time step by rows in CHIUW is faster than Fortran, and we save the values of each time step by columns, Fortran is faster. But in these four options, CHIUW is faster than Fortran. For the Poisson equation, we have the two dimensionals. We choose a square domain and a uniform grid, and use the successive over relaxation method with parameter omega to solve the linear system. So here are the codes. Again, we have to adapt the codes because of the order, row major order in CHIUW and column major order in Fortran. Here the source 10, the boundary conditions that I use, and the parameters. So we have the method converging the same number of iterations in both languages, but CHIUW was faster than Fortran. So the conclusions. CHIUW and Fortran are very similar for these algorithms, but CHIUW is a bit faster than Fortran when we run the codes. Then we decided to choose CHIUW for our fluid mechanics simulations because it was actually better. The performance were actually better than we are thinking. We want to use the parallel processing for the codes in CHIUW is much easier to do than in Fortran. And for the last, CHIUW has some interesting features, like swapping values between two variables, and we don't need to declare all the loop variables. Just some things I think CHIUW is better than Fortran. So thank you for your attention.
All right, thanks, William. That was a good talk. And so now I guess we have a couple of minutes here for questions. So I will open it up for questions. And so I see Brad's got his hand up. So can you go ahead, Brad?
Yeah, I had a question about some of your comments about row major versus column major order. CHIUW actually has at times had experimental features which allowed you to declare your arrays in column major order if that's what a computation preferred. And I was curious whether the computations you're looking at have any natural preference for row versus column major order, or whether the memory layout really doesn't matter to you computationally and numerically.
Actually, it does not matter.
Okay. Yeah, so the reason I was wondering was, I think it would be possible in CHIUW for sure if somebody had a computation where they really preferred column major order to request that we support column major order arrays. And again, we've had prototypes for that. So if you had a computation where you were like, gosh, I really wish CHIUW's arrays were not row major order, I think that is something we could look into more. But it sounds like in your case, maybe it doesn't really matter, that you're happy with what the language gives you and are willing to work with either one. So thanks very much. And I see a comment from Nelson on the chat confirming that it's not so much of a problem to change the code to adjust. Thanks.
Yeah, and I had one question as well, Willian, about so I feel like Brad's question there may have proven this question not particularly interesting, but I was just curious if you'd tried using Chapel's Fortran interoperability to get the best of both worlds here. Like in the case where Fortran was performing better, you could maybe use Chapel's parallelism to call out to Fortran. I was just curious if you experimented with that at all.
I use just serial codes for Chapel and for Fortran. I'm starting to learn both languages about 6 months. So I'm a beginner in both of them.
Okay. Okay. Yeah, that makes sense. Thank you. Yeah. All right. Yeah. And I'm seeing Nelson say that there was no interrupt, but so Brad's got his hand up. So go for it, Brad.
Yeah, I had one other question. So at the end of your talk, I saw that you are planning on going forward with more use of Chapel's parallel features. And I was curious whether you anticipate using those just like on a desktop shared memory system, or whether you think you will also run on larger distributed systems like a cluster or supercomputer.
We're thinking to using a GPU for a desktop.
Okay. That's good to know. Yeah, our GPU team is always interested in users who are interested in making use of GPUs and seeing what kinds of computations they want to use on them. So that'll be interesting for us to learn more about what you're doing there and what your initial experiences are. And that's, I guess, a good opportunity to plug that we've got a GPU session coming up in just a bit today as well. Okay, great. Thank you very much.
Thank you.
Okay, so thanks a lot, Willian. That was an interesting talk. And I think we're coming to the end of session 4 here. And so I will pass it back off to Engin before we start our break.